How do you get the mark? Is that on?
Hello everyone, welcome to the...
Hey everybody!
Hey everyone, welcome to the 8th WMC prize giving. This started in 2018, and I'm sure you're all anxious to receive your prizes and find out where you placed. So of course we're going to do that last. And we're going to start with opening remarks from Professor Chetty, who's the Dean of the Faculty of Science. Prof,
So, good evening, teachers. I've got to recognize our teachers to start with. You've done an awful lot of the hard work in preparing our learners, our successful learners for today, and a very warm welcome to our successful learners. To Wits University, you coming in as high school students, primary school students as well, and at some stage, I hope in the near future, we can welcome you as students here at Wits. So that's a long way ahead of you, but certainly in your success in the Wits Maths competition, I think you're already doing exceptionally well with your studies, and I hope and expect to see you here sometime soon as a fully fledged student at Wits. So the Wits Maths competition began in 2018, as you've just heard from Jonathan, and the colleagues that have been quite involved in putting this together is Dr. Jonathan Kariv, Dr. Ida Kekiante, Dr. Pravesh Ranchad, who you might mistake to be a student, Professor Musa Manzi, who's not here, and Dr. Celeste Johnson, who's been here at the very beginning. So I just want to thank our colleagues for setting this up, and it's fast becoming quite a prized program here at Wits. Wits is a very large university with 45,000 students, many different activities, many different programs and initiatives, degrees, and so on that we award. But the Wits Maths competition is certainly gaining in status since its inception. 2018, we had only around 900 participants, and now 19,500, so more than a factor of 10 increase, which is quite significant. And this time around, we've had the exam papers translated into isiZulu, Sesotho, Afrikaans, and French. So we're obviously making a big effort to reach to different parts of the country, but also beyond our borders. And I'm so delighted to see now that the program is attracting quite a large number of participants from countries from across Africa. So the aim of the program is obviously to identify young talent from very early on, and we make a big effort. The team does make a very big effort to consider students, learners from previously disadvantaged backgrounds. That is important, that we give everybody an opportunity to be exposed and to opportunities in mathematics. And this is exactly what the Wits Maths competition does, is to develop a vibrant community, Olympiad community, because we want Wits to be seen to be a hive of activity, a leader in developing talent for the International Olympiad. But more importantly, and this is what I'm so excited about, is that the Wits Maths competition does create this opportunity for solving of interesting maths problems. I've had a glimpse of some of the exam questions. I got to say that they're not all that easy. I got to ask some of the examiners to tone some of the questions down, I think. I thought some of them were a little bit challenging. But it instills critical thinking in our learners and creating the widest possible opportunities and reaching out to a very wide range of students. So it's really to foster love in mathematics. Mathematics does not have to be the barrier that I think a lot of students see it as being. It is fun. It is a very natural subject. It's a natural way of thinking about the world in which we live. Mathematics developed in a very natural way. It shouldn't be such a huge barrier to engage with mathematics if students, learners can be given the opportunity to be excited. And I've always seen mathematics as a fun subject. I think if it can be approached in a more interesting way, in a more exciting way, in a more entertaining way, intellectually entertaining way, we can attract many more students into mathematics. And as Dean of the Faculty of Science, you will know that this is so important for my advancement of the faculty. Every single student in the Faculty of Science and the Faculty of Engineering, the built environment, has to take mathematics, and so without mathematics, no chance for success at the university. So mathematics is a foundational subject at the university already. So just a very quick word of thanks then from me. I've acknowledged the founders who've put this all together over the past 7 years then. Our sponsors, we're obviously very thankful to Jane Street Capital, which is a company based in New York. Alan Gray, of course, you know of this investment company in South Africa. Sharp, and of course Wits University itself has contributed to the success. And I do want to recognize Mr. Trevor Muller, who has donated a significant amount of money to the Faculty of Science, which has now been allocated to the success of the program. And unfortunately, Mr. Muller could not be here today. So we are part of the plan. We do have a new 5-year plan from 25 to 2029, with a whole new set of goals and plans for the future, principally set on expanding our participation rate across the country, across the continent, but also to increase the number of sponsors so that we can have many more prizes. And today, of course, we are going to be recognizing many of the winners in these various different competitions. I'm glad to say for the very, very first time we have a Wits winner, which is quite nice in itself. It also shows, that's at the undergraduate level, it also shows that we've been very impartial. There's been no kind of bias in terms of selecting the winners. Of course, I will insist on a very impartial process to decide on the winners. So this would not be possible, colleagues, without our many regional coordinators. We have from Namibia, Aubrey Goa Goseb, from Northwest Province, Kayla Hatting, from Nigeria, Godwin Udom, from Rwanda, Theoneste Zanza Barinda, from Cameroon, we have Joseph Domgai, from Ethiopia, Esther Ogena, from the Western Cape, Liam Becker, from the Eastern Cape, Linda Emery, from Mpumalanga Province, we have Lizanne van der Merwe, from Botswana, we have Matthews Masole, from KwaZulu-Natal, we have Taryn Locke, and finally from the Limpopo Province, we have Teboho Kalili. Many of the colleagues are connecting online. I do want to acknowledge the very critical role that our coordinators have played in putting all of this together. And then finally, it is the exam question setters. This must be quite a challenge, and many of the questions are unique. You're not going to find the questions on a quick Google search, I would imagine. So it does require a fair amount of creativity and thought on the part of the exam setters. I want to acknowledge Dylan Nelson, Evan Sneyman, Gabriel Diamond, Gayleen Kramers, Graham Evans, Henry Gonin, Jacqueline Fenter, Jacques Duplessis, John Smith, Kathy Meller, Lara Gavin, Leone Offmeyer, Liam Becker, Danielle Klein, and Carlisle Stewart. So thank you very much indeed for managing the exam process with the integrity that's required. It is a huge effort. There are boot camps and training sessions that are set up, but all of the engagements with schools from such a broad range of geographical locations, this is logistically quite a huge effort, and it does take a bigger effort on the part of volunteers. Nobody's being paid for this. And so I do want to close then by saying how proud I am of the team for putting all of this together, led by Dr. Jonathan Karev, but supported by an admirable team. And long may this continue. I'd like to see this grow from strength to strength, and in particular, I'd like to see and track the winners of the competition, and hopefully some, if not all of you, will find your way to Wits at some stage in the near future. I thank you and congratulations once again to all of the winners.
Okay, thanks, Prof. Chetty. So Prof. Chetty mentioned our sponsors, and we're going to have a few words from them now. And we'll begin with one from Jane Street. They sent a video, and then Andrew from Ellen Gray will take over from that.
Coming into Jane Street, I was definitely expecting to be surrounded by amazing people, but I was blown away by their curiosity and dedication to the work.
The Jane Street internship is an 11-week program spanning trading, tech, SP, research, institutional, and PDOE, where we teach interns about finance, about trading, and about Jane Street. It's an amazing opportunity to learn in a high-paced collaborative environment and to meet people who are talented, but also very humble.
You don't need a background in finance to be a trading intern. You also don't need a background in functional programming to be a dev intern. Jane Street is confident in our ability to teach you anything you need, as long as you're eager to ask a lot of questions and open to learn.
I was scared to ask questions because it's admitting that you don't know something. Eventually, I learned that people really value questions here, and asking questions is a sign that you're a curious person and excited to learn.
The thing that distinguishes the Jane Street internship most is our educational breadth. I think I'm not kidding when I say most interns during the summer learn more in their 11 weeks than an entire year in college.
Jane Street interns come from all different countries and colleges, so it's really interesting to see the different ways that we might address the same problem. Not only did I get to learn from them, but they always challenged me to think outside the box.
I learned a lot of really fascinating things during my Jane Street internship, and some of my favorite were understanding the intricacies of how markets work, including how prices are determined and what exactly happens when you submit an order.
I worked on 2 modeling projects with data sets of different sizes. I got to present to a group of full-timers and answer their questions, which made me feel like I was an expert.
I got to do a research project on the bonds desk, and my mentor showed me how they integrated my project into their trading strategy, and it felt like I made a genuine impact.
My internship experience was jam-packed, very intellectually stimulating, and a lot of fun.
Jane Street puts a lot of thought into planning events that will help you meet people from all around the firm and really get to know them.
I came out of the internship feeling ready to tackle anything, and it was a constantly interesting and challenging experience.
What I most enjoyed about the internship was being part of the Jane Street culture, where everyone is a problem solver and is trying to do things the most efficient way possible. It was really rewarding to work at a place that is not just doing better than the game, but is actually changing the game.
Cool, hi. Tough act to follow. So good evening, everyone. I'd like to start first by congratulating everyone in the room, specifically the students, but also Wits themselves for hosting yet another successful edition of the WMC. Now, I'm sure quite a lot of you are wondering, who is this guy and what does he want? So by way of introduction, my name is Andrew McGregor, and I work for a company called Allen Gray. But I've also sat through my fair share of maths competition prize givings. And that means I know that you guys want one thing from me, is to keep it short, so I'll try. Okay, but let me just tell you a little bit about what I do. So most people in the world are quite busy. Unless they work in markets or finance, they don't necessarily have a whole lot of time to manage their own personal finances, especially if it involves doing lots of research on what to buy, what to sell, all those kinds of things. And so when they get paid at the end of the month, they give a portion of their hard-earned money to companies like us, and they ask us to manage it for them. And what we try to do is we try to grow their savings faster than the average of what they could do if they gave it to someone else. And it turns out this is an extremely difficult problem to solve. But when you actually think about working in investments, so what I've told you, what do you actually think? You're probably thinking something like Wolf of Wall Street, The Big Short, fast-paced traders shouting at each other from across the exchange floor. But actually, this is pretty far from the truth of what my job is. I just do research, really. I spend most of my day reading and learning about new things and about the world. Just a couple of examples. Last few months, I've learned about neural processing units and how they power artificial intelligence on devices like this computer in front of me. Why global uncertainty is pushing central banks to increase their gold holdings in their vaults, and also about the interesting dynamics of the Chinese jewelry market. And once that research process is done, I'll write a report and I'll make recommendations to the people above me, which then structure portfolios and ideally grow your money. And that sort of brings me on to why I'm here. The difficulty of this problem is something that is constantly evolving, and as a result, we are trying to find super smart people. You guys. So because this job is very poorly marketed, I'm trying to come here and show you that this is perhaps something other than actuarial science or comp sci or high-frequency trading as just another option. I don't expect to have convinced you. about this, but I do hope that I've at least planted a seed and that I've given you something to think about. And then you can come either talk to me afterwards if I haven't already run to catch my flight, because unfortunately I have to leave at some point. And then, but if I'm not here, you can always ask John for my email address, and we can have a chat. Yeah, thank you.
Okay, thank you, Andrew. Our next speaker is also Andrew from Sharp Calculators. Andrew.
Good afternoon, evening, everyone. I just want to say congratulations to all of the students that I see in front of me, as well as the parents. I know that you've been very involved in your child's education. You've probably been pushing a lot from your side as well, but a huge congratulations to everyone. It's exciting to be in a room full of the smartest people, so well done. My name is Andrew as well. So I'm currently the relationship manager for Sharp Calculators South Africa. I will be the new brand manager for Sharp Calculators. And I quickly wanted to take a moment to just share what Sharp's been doing and talk a little bit about their education program. So Sharp have been running an education program where we are trying to improve mathematics in South Africa. As you know, we are not anywhere close to the top in the world in terms of mathematics. In actual fact, we are basically at the bottom. And we are working hard with various organizations invested in education to try and make even the smallest difference. I don't know if students, you can let me know, I don't know if you've ever gone to a website called Math at Sharp, where you've downloaded free math worksheets. If you haven't, you are welcome to make use of them in your next year's academic year. I know that you want to take what you've achieved this year and continue into the following year. So there's free downloadable content, worksheets that have been made by maths teachers. I myself was a matric maths teacher for 15 years before I started working for Sharp. So I'm not just some salesperson from SMD Technologies. I'm a maths teacher, and I spend a lot of my time doing workshops, doing training. What we've noticed with teachers and students is a lack of calculator skills. And I'd like to challenge the learners in front of me. The calculator that you use, do you fully know how to use every feature on that calculator to its... And the answer probably is no. And is the company that you are using, are they making the big efforts to make sure you know how to use all the features of that calculator? And so part of what Sharp's been doing is they've developed a lot of content, not just worksheets, practice exercises, past papers, but they've got a YouTube channel full of videos showing you how to use the calculators to their full potential. I'd love for you to take a moment and check it out. So if you had to go onto YouTube, Math at Sharp, have a look. So we've got a new calculator called the ELW535, and it's got a whole bunch of features that you've never used before, like infinite summary of statistics, infinite table mode. So those who work in table mode, the seniors, grade 10s, 11s, and 12s, that when you do functions, you'll know that your calculator is limited to a maximum of 10 values. You're now working on a calculator with infinite table mode. And that just means that it's going to continue generating X and Y coordinates. And if you think about the application of that in various math examples, you'll realize how helpful that is, as well as a summary of statistics. So we are the only calculator brand to produce a summary of stats. So just by pressing it would be alpha and 8 and 0 to get your statistical values. It's showing you a very comprehensive breakdown of all of the stats. So you're looking at the total number of values put in, the mean, standard deviation, as well as the whole five-number summary, all in one go. And it's the only calculator to do that. As well as, it's got a whole bunch of features. Go onto YouTube and check those calculators out. I think it will help a lot of you next year. As I said, it's a new model, so a lot of people are not yet aware of it. But I think it's going to help you in your learning in next year. Okay. All right, again, I want to say congratulations to every single one of you. Well done. And it's amazing to be in a room full of such incredible people that have worked extremely hard to get to where you are. So well done. Thank you.
Hey everybody, I'm Pravesh from the School of Computer Science and Applied Maths. And when it comes to students like you, people who love maths, there's sort of two major reasons I can think of. One is that it's just intrinsically fun, right? You just feel good when you solve something that's difficult to solve, okay? But another reason, and the primary reason for me, is that maths enables you to do really cool things, right? There's just a lot of stuff out there that if you're not sufficiently able to do maths, you just won't be able to do these incredibly cool things. So I'd like to introduce Dr. Stephen James from the School of Computer Science and Applied Mathematics, who's going to tell you about some of those incredibly cool things.
All right, hi everyone. Thanks for coming to listen to me. That's the only reason you're here, right? I know it's been a long day, and I know that we're all here for the prizes, and I've seen the medals, they're very pretty. So I'm going to keep it short. We're going to do like 2 hours, and then a break, and then another 30 minutes. And so hopefully by midnight we can get to that. Okay, so I'm going to talk to you today about some things that I think are cool, that are useful for mathematics, or rather ways that mathematics are useful for the things that I care about. So my background, I am a computer scientist. I'm not a mathematician, and so basically every single person in this room knows more about maths than I do. But nonetheless, I'll show you what cool things you can do with the little maths that I know. So just very quickly, some background. I kind of co-direct a research group at the university. We're called the Rail Lab. And we focus on robotics and artificial intelligence. That's the thing that I care about, that I'm passionate about. And so what I hope is that in between 5 to 10 years from now, I will see everyone in my group doing their masters and doing their PhD. So that would make me very happy. Okay. So the talk that I've got is a bit strange, and it's broken into 3 parts. So please raise your hand if you know what Minecraft is. Does everyone know what Minecraft is? Almost everyone. Everyone who doesn't know is probably over the age of 50, but we'll get into what Minecraft is. Okay, so in 3 parts. First part is going to be, I'm going to talk about dirt, because I think that's cool. We're going to talk about dirt in part 1. And then after the dirt, we're going to talk about this thing called Minecraft. Minecraft is a video game, for those who are not aware. We'll talk about Minecraft. And then part 3, we'll talk about robots. So dirt, Minecraft, and robots. And I promise it will make sense at the end. Okay, part 1, dirt. Very interesting. Okay, so it starts off with this French mathematician. His name is Gaspard Monge. Excuse my pronunciation, but his name is Gaspard. He lives around the 1700s in France. And this is around 1781 that he is working on trying to, as an engineer. So he's working on building ditches and rivers and fortification and castles and all these kinds of things. And so he's quite a practical guy. And he comes up with this problem. He says, okay, well, we're trying to build like a fort, right, made of stone or whatever. What's the best, most efficient way to do that? And so kind of the problem he comes up with is essentially, imagine you've got like a pile of dirt or bricks or whatever it is, and now imagine you've got like a hole, and you want to fill the hole with the dirt because the hole is there, and for whatever reason you want to do that. Or you could think about it in any other context, like you've got some bricks and you want to build a castle. So now you need to take each brick and put it where it would go in the castle, or you need to take each piece of dirt and put it somewhere in the hole. And so the question that he wants to find out is, what's the best way of doing this? And by best, he means like least effort. Like we want to get the dirt into the hole, but we want to do this as efficiently as possible, not wasting any time, not wasting any effort. So this is the question that he's interested in. How can we do this mathematically? And then if we can come up with a math solution, then hopefully we can go do that in practice and make our systems more efficient. So the question is, how do we do this? Okay. So what he's looking for is something that he calls a transportation map. Okay, so when he says transportation, he means literally we need to transport the dirt from one location to another location. And by map, what he means is we're trying to move, for instance, each piece of dirt. Let's say we break down the dirt into like a 5x5 grid. Let's pretend there's 25 pieces of dirt. We need to move each piece of dirt to some location somewhere else. So you could imagine on the slide over here, what we're seeing is like a piece of dirt moves from some location in the dirt pile to some location in the hole pile. And another piece of dirt moves from somewhere else to somewhere else, and you want to move every single piece from one location to another. You want to make sure that A, you move all the dirt into the hole, so all the dirt is gone and the hole is full. And also, obviously, each piece of dirt will go into its own unique place. You can't have like two pieces of dirt occupying the same physical space, so each of them needs to go into its own spot. Okay? So this is the kind of map that he imagines, and he wants to know what is the best map. And again, by best, he means the one that makes the fewest amount of moves, essentially. Like, if I have to move a piece of dirt from here all the way here, well, that's a lot of effort. But if I have to move dirt from here to here, that's a little effort. So we want to minimize the total effort that we're going through in order to move the piles of dirt. So you could consider this map, and I haven't drawn all the arrows from each piece of dirt to each hole location because I couldn't be bothered, but imagine that was one case. But now you could also imagine like another map which moves different pieces of dirt to different locations, right? So you could have like this map or any other map. There's like combinatorially many ways that you could do this. And everyone in this room, because you've done, maths and you're really good at it, I'm sure you can tell me how many different ways you could move all the pieces of dirt to all the possible locations. And there is no prize for doing this, but you can tell me afterwards what that answer is. Okay. Cool. So this is kind of the problem that he sets out to achieve is what's the best map? What's the map that works, that uses the least amount of effort to make this happen? Okay. And this becomes known as something called optimal transport. Optimal in the sense of least amount of effort used, and transport because literally moving stuff from one location to another. Okay? Now, the example that he's imagining is things like moving dirt into holes or moving bricks into castles. Whatever the case, it doesn't actually matter what the stuff is. It can be like any stuff into any other stuff. Okay? So dirt into holes, or more abstractly, whatever into something else, like some kind of transformation. So this is called optimal transport. Okay? And actually, you don't learn about this in university, so I'm giving you a preview. It's not in our curriculum, so hopefully you follow me with what we're about to go through. Okay, so we're looking for this kind of transport map that tells us how to move pieces across, and we want the best possible one. So, for instance, in this example, each grain of dirt X, we'll say for each X, it's going to move to location T of X. Okay? And as I've said, we want to do this as efficiently as possible. So we're going to have the total cost, the effort, be minimized. And also, the important thing here is like there needs to be like a conservation of mass, which is not like saying all the dirt gets moved, we don't lose any dirt, none of the dirt disappears, all of it ends up in the new place. We don't lose anything along the way. Okay, so this is what the problem of optimal transport considers. Okay, So this is like the mathematical formulation, and don't worry too much if you don't understand what's going on the screen. I don't understand what's going on the screen. Okay. ChatGPT told me that this is it, so I just copied. I wanted to look clever for everyone. I didn't want to have pictures of dirt, but you know, this is what it says. But fundamentally, what's happening, and I'm sorry I don't have like ways of drawing, is basically there's two things. There's the thing on the top that says min, and that's like we're trying to minimize something. The thing we're trying to minimize is a cost. That's what the C is. The C is the cost. And we're trying to find that T. That T is the transportation map. So find the T such that the cost of moving all the stuff from one location to another is minimized. Find that T that gives you that minimum. Subject to some constraint. And what is the constraint? The constraint is basically this conservation of mass that says everything that I move across ends up over there. So all the dirt leaves the dirt pile and it all ends up in the hole. That's what that constraint says. And you solve this, or you try to solve it. Now it turns out that you can't actually do this. And so for 150 years, people tried, failed. There's a whole bunch of technical reasons why this doesn't work. If you're interested, it's to do with the constraint and the nonlinearity of that. Nonetheless, whatever the case, just too hard. Just too hard doesn't work. Okay. It does work in very specific situations though, and I'll show you one right now, and those situations are very useful for real world things. Okay. So let me show you an example of where things do work and you can work out a perfect solution and everything is great. So it works in the case where you're trying to move a discrete finite amount of things from one location to another, and you're trying to do this kind of like one-to-one assignment. So here we have an example. Let's say we have 3 people, Alice and Bob and Charlie, ABC, and there are 3 tasks. So what we're trying to do here, this kind of optimal transport situation, is we are trying to move people to tasks. And so what that means is assigning tasks to people. And now let's pretend that each person can do any of the tasks, but it takes everyone a different amount of time because some people are better than others. You know, if I have to go cook, it's going to take me a long time. If my wife has to cook, very quick. So maybe you don't want to give me the cooking job, you want to give me something else. Okay, like watching TV, I'm very good at. So I will watch TV and she will cook and then everything will be great. Okay, please don't tell her I said that. Okay, so this is the kind of situation that we have, and we want to know what is the optimal transport, so moving from people to tasks. Optimal now means we want to minimize the cost. In this case, we want to minimize the total amount of time that it takes to do all the tasks. We want to keep that to a minimum. Okay, so the sum must be minimized. Okay, so here's how we do it. There is an algorithm to do this called the Hungarian algorithm that was invented like 100 years later and then reinvented another 50 years later. But I'll quickly show you how this works. It's magical. Don't ask me how it works, but it does work. So I'll show you. Okay. Step 1 says, look at each row, subtract the smallest value from that row. So in row number 1, you can see that the smallest value is 12. Row number 2, the smallest value is 13. In row number 3, the smallest value is 15. So from row 1, we're going to subtract 12. From row 2, 13. From row 3, 15. So let's do that. Okay, so we get this. Okay, I've just subtracted. Even I can do that. Okay, so now what the question is, what we're looking for at the end, when we stop doing all of this, is we want to find a 0 in every row and every column. So that's what we want, a 0 to be present in every row and every column. And so we can see that at the moment we're not quite there, because we do have a 0 in every row, but that's column number 2. Column 2 does not have a 0. So we're not done yet. We have to do some more stuff. So now let's look at that problematic column. Okay? So the problematic column, column 2, there are no zeros. So now what we're going to do is we're going to look in that column, take the smallest number. That smallest number is 2. And then we're going to subtract it from the column. So we're going to just reduce that column by 2. Okay? So now it looks like that. Very easy, right? Like arithmetic. Okay? So now what we've got this. Now what we can see is that every row and every column have a 0. So now there's another step. The next step says, try cover up all the zeros by drawing lines, straight lines, as few as possible. So try to draw lines through this, horizontally or vertically, to try to cover up as many zeros as you can. Okay, and we want the fewest number of lines. Okay, so this is what we're going to try to do now. So draw a line to cover all the zeros, but as few lines as possible. So we can do this. Hopefully you can see like a solution here. You can do this in 2 lines. You draw a line down column 1 and a line across row 2. And at that point, we've covered all the zeros. You can imagine, I've left them on there, but like you can imagine, it's like a solid piece of paper. You can't see the zeros anymore. Okay. So are we done? Apparently not. So now it says, okay, well, we did that, but we took 2 lines to do it. But we've got like 3 people and 3 tasks. So that's not good. We wanted 3 lines, but it only took us 2 lines. So now we have to do something else. So what are we going to do? We're going to find the smallest number that hasn't been covered by the line. Okay? The smallest number that hasn't been covered by the line is the number 1. Okay, it's over there. You can see where the 1 is. So now take that 1 and add it to the intersection of the lines. So look where the lines intersect and add it to there, to that part. Okay? So now it went, maybe too fast for you, was at 8, now at 9. 8 plus 1 is 9, as I tell my first year students. So now we have that. The next step then says, for all the other uncovered numbers, subtract that number. So minus 1 from everything else that's not covered. Okay? So we're going to look at all the numbers that aren't covered, minus 1, and you get that. Okay. Now we can look again, and then we can say, okay, how many lines does it take in order to cover all the zeros? And it turns out that no matter how you do it, you need 3 lines to cover all the zeros. There's no way to do it with 2, you need 3. So at that point, we need 3 lines. We are trying to allocate 3 people to 3 tasks. 3 equals 3 equals 3, so we stop. And now we can go to the assignment. And the assignment basically says, look at all the zeros. That's your allocation. Okay, so let's do that. So let's look at all the zeros. Okay, so for Alice, what's her role? Well, there's only one option. Okay, Alice will get task 1 because there's a 0 there. Now let's look, we'll skip ahead, let's look at Charlie. Charlie, we can do task 1 or task 2, but Alice has done task 1. So task 1 is off the board. Therefore, we have to give task 2 to Charlie. And then Bob, who's in the middle, can do task 2 or task 3. But task 2 has already been taken by Charlie, so Bob will do task 3. Okay, and that's it. That's the sum total of everything. This is the allocation, and the minimum cost is 43, and you can work that out, that there is no better assignment than this one here. And this works in all of these cases. Okay? But it only works in this like specific case. Okay? By the way, if you're interested in knowing why that all works, ask Pravesh. I don't know. Okay? But it does, I promise. Again, ChatGPT told me so. Okay. So, that's great, but it doesn't always work. Okay? And there's a few reasons it doesn't work, but also what you could imagine is like, that works when it's like 3 by 3, but now let's worry about like, imagine instead of 3 by 3, you've got like a continuous thing. You've got like infinitely many things, trying to move it to infinitely many other things, things get a bit hairy. Okay? So it doesn't always work. And in particular, one of the reasons why it's too hard is this restriction that says every single thing has to go to one other thing is too hard. It's too strong. That constraint is too tough to deal with. Okay? It makes sense when you're trying to allocate people to tasks because you do want one person to do one task, but in general, it's just too hard. Okay? So, that's where things got left off for like 150 years. Okay? And then in the early 20th century, we have a mathematician over here. His name is Leonard Kantorovich. Okay? I hope I pronounced that right, but he is unfortunately dead, and so he can't correct me. But I assume it's Kantorovich. Okay? And he's a mathematician and an economist, and he's working on this problem at a plywood factory. So at a factory that makes wood, and he's trying to work out what's the best way to allocate resources? So we've got like workers and they have jobs to do, but also there's trucks making deliveries, and all of these things need to be accounted for, and you've got trucks coming in, with material that needs to be processed. And how do we best allocate and optimize this whole process so that we can be as efficient as possible in the factory, fundamentally? Okay. And so what he does is he comes up with a different formulation compared to Monge. Okay? He cheats, basically. Now, when a mathematician cheats, basically what they're trying to do is they're trying to make the problem easier. So they change the problem slightly to make it easier, so they're cheating. But you're a mathematician, so you don't say this, so what you say is, I've relaxed the problem. So he creates what's called a relaxed version, which I would call cheating, but they call relaxed. And basically, what this relaxed version allows is for the ability to split things up. Okay? So now, what you're allowed to say is, instead of saying each piece of dirt has to go to one location, you're allowed to split up that piece of dirt if you want. You can say like 30% of it goes here and 70% of it goes here. Alternatively, you could see that as not like that interpretation. You could see it as it's like a probabilistic thing. You could say, with 30% probability, I put the grain of dirt here, and with 70% probability, I put it here. Okay? Whatever the case, they're both equivalent, but he allows for this kind of more flexible splitting to occur. Okay? And this is it. This is like the sum total of what he changes in the formulation, and it turns out that all of this has massive impacts on what happens next. Okay? So, this was the original scary equation that Monge dealt with 150 years before Kantorovich. And this is what the formulation now becomes. Okay, so I'm going to flip back and forth between the two. What you'll notice is that the minimizing thing, you're still looking for that like transportation map. You're still looking for the minimum of that thing. That's basically the same. More or less, if you look between the two, it's kind of like the same thing, more or less. So, still the same problem. It's just that the constraint at the bottom has changed. Okay? So previously the constraint looked like this. It said you have to move each piece of dirt to a unique location and they must all work out and you mustn't lose any dirt. The bottom one says basically the same thing, but now all it says is like the outflow of dirt has to be the same as the original pile, and the inflow of dirt to the hole has to be the same as how much the hole can take. Okay? But it doesn't matter where the dirt goes. It doesn't have to be the case that each piece of dirt goes in exactly one place. They can do whatever, as long as at the end of the day, the dirt gets moved to the hole. Okay? So that's like a very slight change, a very slight relaxation of the problem that just says, as long as it gets moved, I don't care how, I'm not interested. Doesn't have to be a one-to-one mapping kind of thing. Then everything is fine and it works. And that's his formulation. And it turns out, excuse me, that the constraints over here are what are called linear. And because they are linear, you can apply some very clever techniques that are called linear programming to solve this. So if you're here and you're at Wits and you're in first year and you do applied maths, you'll have done linear programming. So, or maybe even in high school, I don't know. I was in high school many years ago. And you can solve this problem because those constraints are what are called linear. Okay? And for this work and many other things, Kantorovich gets the Nobel Prize in 1975 in economics. Okay? For his pile of dirt. This was also ChatGPT. ChatGPT really helps me very much. Okay? So, that's the end of the maths lesson. We don't want to have a maths lesson. It's 6:15. And so, now I'm going to talk about Minecraft. And then I'll show you why I was talking about dirt and now I'm talking about Minecraft. So this is work that we did in collaboration with my student Damien, who's in the corner here, and he's very excellent. And so I want to show you some stuff we've been working on in Minecraft and how that relates to dirt and optimal transport. Okay, so for those who don't know, Minecraft is like Lego, but as a video game. So the point of Minecraft is that there is no point, you just build stuff. And there are blocks, and you can go get the blocks, and there are different kinds of blocks. There's like a grass block, and a dirt block, and a stone block. And then you can use those blocks to make houses, and you can also use them to make tools. And those tools allow you to process other blocks. So for instance, there's a stone block, but you can't get the stone block unless you have a pickaxe, because obviously you can't break a stone with your hand unless you're really strong. So you need a pickaxe. To get a pickaxe, you need to go build a pickaxe with some other resources and so on and so forth. Long story short, it doesn't really make sense, but you just do stuff and you collect stuff and you build stuff. Okay. And that stuff involves having to do these bunch of tasks, like these subtasks of, let's first go smash a tree and we can get some wood, and then we can use that wood to make a pickaxe, and then we can use that pickaxe to go get some stone, and so on and so forth. So the challenge that we have here is to say, imagine I'm watching a video of someone playing Minecraft. So I'm watching this happen. I want to know what they're doing at this particular moment in time. Are they going to get wood? Or are they going to make a pickaxe? Or are they going to mine stone? What is it that they're doing at this moment in time as I'm watching this video? So basically you can see like there's a label at the bottom. It says like skill 1, get wood. Skill 2, make a pickaxe. Skill 3, get some stone. So we're trying to work out automatically what those labels should be for a given video. That's the challenge. You might ask, why should you care? Why is that a thing? Because it's cool, and I don't have to just know. Because, I'll show you later why that's important. Okay, so this is the challenge. On the left-hand side, we have videos. So imagine each of those pink lines is like a video. And then on the right-hand side, what we want to say is, let's break up those videos into like blocks. And in like the first block, maybe you're walking to a tree, and then you're smashing a tree, and then you're building a thing. And then in this video, now you are building something, and then you're smashing something, and then you're walking somewhere, and so on and so forth. So you're trying to recognize the actions that are occurring in the videos. Okay. So why I mention this is because this is nothing more than an optimal transport problem. On the left-hand side, you have videos. But what are videos? Videos are just still images. They're just photos that are one after the other, fast enough that it looks like movement. Okay? So videos are just images. So we've got on the left-hand side a bunch of images. And on the right-hand side, we have some buckets or some holes that you could imagine. And those holes refer to like, am I collecting wood? Am I making a pickaxe? Am I collecting stone? And what I want to do is try to put the image frames, the videos, or parts of the video into the wood bucket, or the pickaxe bucket, or the stone bucket. Okay? And whenever you're moving something to somewhere else, well, you can think optimal transport. What's the best way of moving these images into the wood bucket, the images into the pickaxe bucket, the images into the stone bucket? Okay? So we use optimal transport to solve this problem, and we get something that looks like this. On the top level, that's like the truth. That is what was happening in a particular video. The colors represent the action that the player was taking, whatever that action was. Our method that uses optimal transport is the next row down. It says HISD. And basically what it shows is more or less we can recover exactly what the player was doing at that moment in time just by looking at the images. Okay? The rest of them are just all other research that has happened in the space. So we are better than all the other research. Okay? That's why you should come work in our lab, because we just beat everyone, no matter what. Okay? And so what you get out at the end of the day is this kind of information about having watched this video. Oh, the player did this, and then they did this, and then they did this. Okay. Cool. So I'm going to wrap up now by talking about robots. And at this point, if you're wondering, why the heck are you talking about dirt, and now you're talking about a video game? This is why. Okay. So the robots is what I want to talk about, actually. Okay. So, sorry. Before I start, I want to play a quick video of a baby learning some stuff. Okay. And what I want you to think about is how humans go about learning things. It is the case that like we learn from watching other people, right? Like imagine you took a baby just born and you put it in like a field. Let's say it's a really smart baby like Einstein, okay? You put Einstein in a field, it's very lush, it has all the fruit and food, and there are no predators, and you just leave that baby there for its entire life. I'm not saying you should do this, but imagine you did. The question is like, would that baby ever grow up to invent general relativity? Probably not. Like what would that baby be able to learn in isolation? Probably not a whole lot. we learn a lot from watching other people do, and that's a reason why humanity has made such great progress, because we can learn from others, whether that's from watching them or from visual communication. And so I want to show you an example of that right now.
Young child, notice the gaze looking down at the object, up at the person, down at the object. He puts beads in the cup. The young child doesn't have any linguistic description of what to do. We didn't tell her what to do. She simply watched, did the same thing, and was quite happy with herself. Then I take a camping cup and I do something unusual. I turn it over, squash it with my hand. She looks at the object, the person, the object. And she does the same thing.
Okay, I'm going to skip ahead. That's not a long video, but that's a very cute video. So that's an interesting thing going on, right? Like, you demonstrate a thing to a baby, and then the baby can do that. Or not necessarily a baby, like toddler can do that, okay? Now that's interesting because a human, like a fully grown adult, is much bigger than a baby. Like the arm span is longer, the height is longer, everything is different. The joints of an adult are very different from the joints of a child. And yet a child is able to look at an adult who looks very different, is differently sized and all of that, and still work out what the correct actions are to do in order to mimic that adult. Okay? So what is that? Again, well, that is optimal transport happening on the part of the child. You're seeing a thing, and you're moving the example of the adult doing something, that motion, into the space that you are able to do because your arms are shorter and your body is different and so on and so forth. You're able to make that transformation. You're able to make that mapping from the grown-up to yourself in order to execute that behavior. Okay? And that is nothing more than optimal transport. And why this is important, I think, for robots is because of this. Okay. On the left-hand side is a robot called Asimo. It was one of the first robots that ever kind of like did anything useful in terms of walking around the world. It was invented by Honda. This is around 2002, so before most of you were born. This is what it could do.
I am ready.
Okay, then go for it. With each step, Asimo must adapt and constantly calibrate, using all its computing power and sensors to remain upright all the way. Way to go, Asimo!
Okay, so it could walk up the stairs, which at the time was like mind-blowing, but that's about it. Okay? If you fast forward to today, this is a Unitree G1 on the right-hand side. This is where we're at now. Better than me. Okay, and so why have we reached this point? Well, we've reached this point that we've gotten so good at this kind of thing because we have lots of data of humans doing things. Okay, so I'll play this through. We have videos of people doing things, and now we have robots, and now people and robots are different. Even if the robot is designed to look like a human, the length of your arm is different, the position of your joints is different. But if we can use the same optimal transport theory, then we can learn from human data, from videos of humans doing things, and map that onto the space of robot joints. And then what that means is we can learn from that data. All the videos on the internet that exist of people doing things, we can transfer that onto a robot's body and have the robot efficiently do the same kind of thing a human is doing. And that is the reason why we're seeing these kind of massive gains in robotics, in movement, and things like that. And so I really think that optimal transport as a solution to getting robots to do really cool things in the real world is really a promising way of leveraging all the data that exists of people doing things in order to train our robots to do cool stuff. Okay, so that's not all. Optimal transport is used in everything from the video generation that you see on ChatGPT when you say generate a picture of XYZ, gives you that. That's optimal transport, moving from noise to an image. We also have things of like in genetics and biology, tracking the movement of cells over time, optimal transport, of mapping climate over time, optimal transport, of looking at MRIs of brains and moving the MRI from one person's brain to another person's brain, optimal transport. Okay, so it happens all over the place, and I think is a really cool idea that came about from like a mound of dirt, fundamentally. So let me finish up because I've been talking for too long already, and let me just say that for me, science and mathematics comes about not because you're trying to set out to solve like some really hot problem that like, you know, just you want to solve it because everyone else is doing that. It comes about because you think it's cool. And so my impression of the best kinds of people are the best kinds of people who do things because they think it's cool and they're passionate. And who knows, the next thing you work on might change the face of science. So let me stop there. Thank you very much for having me, and enjoy the rest of the night.
Thank you, Dr. James. So by tradition, the WMC has 2 speakers every year, one from Wits and an international one. So our international speaker is going to be Prof. Artens Said from Tsinghua University, which I've been struggling to pronounce all week. But it's a top 5 university in China. Before that, he was a postdoc at Princeton. And he's going to tell you about why prime numbers and knots have a lot in common. Prof. Said?
Yeah. So, sorry, I gotta get the slideshow going. How do I get it full screen again? If you do the full screen, sometimes is it like Control L? Yeah, there we go. Okay, and then just the down arrow. Okay, sounds good. Nice. Don't look too much at that screen. It's just okay. Sounds good. Okay, so yeah, I was here. I was at Wits last year for PAMO, and I'm glad to be back. So yeah, I'm at the Yao Center at Tsinghua University, which is a university in China, and unfortunately for you, I'm a mathematician. So that means my talk is probably not gonna be able to compete with robots in Minecraft. But one of the things we saw in Steve's talk is that one of the powers of mathematics is that you can look at different things and see similarities and exploit them. And I'm going to tell you about one analogy in mathematics, which I find really cool. So, and this is an analogy between primes and knots. So today I'd like to tell you a little story between a similarity between 2 kind of old theories in mathematics, and those are number theory and knot theory, or 3-dimensional geometry. So I'm gonna try to define what these things are and what their goals are and a little bit of their history, and then I'll tell you why they're kind of similar a little bit. So this analogy, or this kind of like similarity between number theory and 3-dimensional geometry, or knot theory, is a story that kind of emerged through the work of many mathematicians in the 1970s. So to list a few: Mumford, Maser. Sorry, can I ask you to speak? Oh yeah, sorry. Okay. And look there. Okay, sounds good. So I apologize for the people in the room. Yeah, so the work of many mathematicians: Mumford, Maser, Manin, Kapranov, Reznikov, and Morishita. And it's a story that's still being sort of written and elaborated today. And so 1970s in the mathematical world is, quite recent, but it involves 2 mathematical worlds which are much, much older. So I'll tell you a little bit about number theory. So number theory really is the study of Z. So those are the counting numbers. So the negative numbers, 0, 1, 2, 3, 4, etc. And equations involving them. And it's one of the oldest areas of mathematics. I mean, there are tablets in cuneiform that we found in the area of Mesopotamia from the Babylonians. And you see it through all kinds of ancient cultures where people have been studying and recording their solutions to equations involving integers. And that's the study of Diophantine equations. One reason why they would do this is because if you're building if you're doing architecture with like a standard unit of building, and you want to make shapes, those shapes have to have a certain multiple of that unit of building. And so you're kind of constrained in what kind of shapes you can use. So it's a very old subject. And sort of its fundamental kind of object are prime numbers. So those are the numbers whose only divisors are themselves and 1. So So for example, 2 can only be divided by 2 and 1. 3 the same way. 4 can be divided by 2. And 4 and 1. And there are infinitely many of these prime numbers. And the interesting thing about prime numbers is that every single number you can think of can be sort of factored uniquely as a product of primes. So prime numbers are sort of the atoms of the number world. And one thing which I like about sort of mathematics is that the story of how ideas came about are very, very interesting and riveting usually. And one anecdote about this is that there was a sect of Greek mathematicians led by Pythagoras, of the Pythagoras theorem, who kind of created a sort of religion where they believed that everything in the world could be explained by sort of whole numbers and harmonic relations between them. And there's a very famous story. So someone discovered that there were numbers that were not rational. The square root of 2 is one example. And that person presented his proof to Pythagoras, and it went so much against his worldview and their whole theory of the universe that Pythagoras had him killed. So mathematics can be dangerous sometimes. The second sort of world in this analogy is knot theory. So this is also a very old area. So what are knots? You can think of a knot as just taking a piece of string and tying its ends together after doing some really weird path in space. And so you can make all these kinds of different knots. If you take many pieces of strings and you go randomly in space and wrap them around each other, you'll get something that mathematicians call a tangle. So I haven't written one here. And knot theory kind of arose kind of obviously, right? I mean, there are many applications of taking rope and sort of going through space with it and seeing what you get. So, you make knots for sailing, they're used for climbing, for braiding, weaving. And also there are many mystical things with knots. At the end, I'll go back to one of these things. And knots were also thought of as atoms. And so in this other sort of very old world, there was a theory that tried to explain the universe using knots. And this goes to around the 1800s. And there was an attempt, so back then physicists thought all of the universe was kind of like this sort of fluid that was called ether. And so, how do you get matter out of, if everything's the same, how do you get matter? How do you get different things? And they kind of came up with this idea that if you took ether, this like fluid, and it was sort of, it circulated in certain braided ways or certain knotted ways, it would make something stable. And those stable things would be the atoms. And many famous people thought about these things. So Lord Kelvin, who did a lot in thermodynamics, Maxwell, who kind of wrote down all the equations for electricity that we sort of use today, and Tate actually really worked with this theory. This is Maxwell, picture there. And what they try to do is write down all the possible knots you could write down in order to understand all of matter. So that was their gig. As it turned out, this theory was not very good, the theory of ether, and therefore their tables of knots. But for mathematics, these things are very interesting and we can study them. And so here's the sort of metaphor that I'm going to talk about today, is that knots and primes seem to be governed by the same rules. There's no real bridge between these two worlds, but somehow they seem to kind of behave in similar ways. And so I'll try to give you a sense of what this phrase sort of means in two examples. So one thing you can do to sort of test this like sentence, which is kind of sketchy, is you can look at a random number and you can look at a random knot or tangle. So a random number you know how to take, we pick one. What about a random tangle? We write down a bunch of digits, right? That's how you get a random number. To get a random sort of tangle, what you can do is take a bunch of strings that are open, you lay them on a table and you sort of tangle them over each other. And then you look at the ends and you tie them with the ends that sort of lie at the first level and the second level together and so forth. Sometimes you'll get something which is connected, like this, so you'll get a real knot. Sometimes you'll get a bunch of knots that may be knotted with each other or not. So for example, if you had like just a flat piece of string on the bottom that you don't use, you'll get a separate just loop. Okay? And, oops. So yeah. What you can do is then look at sort of various statistical questions about how you decompose these primes into knots. So once you do this process, you'll get a bunch of tangled knots. And the metaphor, the primes and the knots are the same thing, okay? And what you can do is look at statistical questions that involve the decomposition of tangles into knots and primes, and numbers into primes. And so you can do these experiments on a computer. You can take a random, for example, 100-digit number, and you can ask, is there only, like, when is it prime? Is it prime or not? And you can look at these statistics and record them. And you'll get a number, and you can ask, are there exactly two prime factors? And you can look at the percentage you get. Is there a large prime factor, one which has more than half of the digits of this thing you started with? So in this case, 50, more than 50 digits. And you can do the same thing for knots, or for tangles that you obtain in this random way. And it's really freaky, but if you do this on a computer, you'll see that the numbers match. Like if you take a large enough sort of sample. And there's no reason for this to happen, right? I mean, I told you about numbers, I told you about knots, like these weird theories from antiquity that aren't true. But somehow in mathematics, it seems like these things are governed by the same thing. You can test this even further. So once you take this random sort of tangle and you get these random things, you'll get a bunch of knots which are knotted around each other in weird ways. And so far we've just said, oh, well, how many knots do you get inside them, right in this table? But we haven't taken into account how the different knots are kind of linked around each other. And in fact, it's really weird, but this analogy goes even further somehow. So yeah, when we made those random tangles, it was possible to get a bunch of knots that are all tangled together. And one way of measuring the tangling between two knots is something called the linking number. So if you have two different knots that are kind of linked together in space, what you can do is count how many times one winds around each another. Okay? So for example, here I have two loops in space, and I've just linked them once. So the linking number is 1. And then the other one, I've kind of like linked it once and then went around once more. So the linking number is 2. So there's a way of getting sort of a number out of that reflects how things are linked together. And a question you could ask is, what feature in number theory kind of captures these tanglings? And I'll make a detour to explain this. And it's through something called modular arithmetic. And so modular arithmetic is really clock arithmetic. So if I tell you what time is it in 24 hours, right, it's going to be the same time as it is now. And you can make number systems that sort of have this rule embedded. So you can take numbers up to remainders when you divide by something which we call a modulus. For clock arithmetic, that modulus is 24, because the day is 24 hours. So for example, if you take the modulus of V5, the possible residues you get are, possible hours you get are 0, 1, 2, 3, 4. Okay? And with these numbers, it's possible to do arithmetic. So it's possible to add them together, to multiply them together, sometimes to divide in these things. And so you get lots of small versions of the usual arithmetic you know. And the link with, the relation with linking that we just saw is about looking at squares in these systems of small versions of the usual arithmetic. So not all numbers are squares, just like in the integers. And you can sort of record how many of the numbers mod 5, for example, are squares, right? So one way you can do it is look at 0, 1, 2, 3, 4, and then square each of them, and record, after you divide, you find a remainder by 5, what do you get? So 0 squared is 0, 1 squared is 1, so you record those two, those are quadratic residues, those are squares, mod 5. Then you take 2 and you square it, and you get 4. So 4 is also a square mod 5. You take 3, you square it, you get 9. That gives you 4 again, mod 5. And if you take 4, that gives you 16, it gives you 1. So not all numbers are squares, and those are all the squares you get. And in general, if, this took a bit of time. We need to go through each number and square it, or at least half of them, because there's a negative somewhere, and we can record them. But in general, it's very hard to tell whether a given number is a square mod another large number, because you'd have to go through all the hours of the day, basically, and square them. But the metaphor that like the prime knots analogy suggests is that the question of whether the linking between two knots, the linking number between two knots is even or odd, is like if you take a prime and you consider and ask the question whether it's a square modular another prime or not. So that's the link between the two. And it turns out that if you make this metaphor, there are two very natural theorems, and one of them is very complicated, the one on the right. So the linking number, right? I've just counted how many times one knot links around another. I can ask whether the first one links around the other or the second one links around the other, and those things are symmetric. So the parity is the same on both. On the other hand, if you look at number theory, this is one of the first very, very difficult theorems in number theory. And it was studied by Gauss, who's pictured there. Yeah, very great guy. He's considered probably the best mathematician ever. And he found 8 proofs of this thing. So this was probably his favorite theorem. And it's that if you have one prime, it's going to be a squared modular another prime, if and only if that other prime is a square modular of the first one. So you have these two systems of arithmetic, right? These small little toy clock models, modular one prime and another, and somehow they know about each other a little bit. There's a link between them. And in this analogy, this link is explained by the fact that the linking number is symmetric. So we can do an experiment with 5 and 7, right? So 7 is 2 mod 5, and in our list, right, 2 is not a quadratic residue, and then you can go home and try to see if 5 is a square mod 7. And you'll see it's not. You can do this with many primes. There's a little bit of a caveat here, so that's my handwriting. I am a doctor, so it's bad. And so, okay. Yeah, and to end, this kind of analogy is part of a larger subject called arithmetic topology, which touches on many aspects in mathematics. The analogy is still mysterious, but somehow to study different things, you draw inspiration from one side or the other. A little bit like in Steve's talk, you drew inspiration from optimal transport to understand all these varieties of different problems. Except here we're kind of missing the optimal transfer theory, the real theory that tells us how to go from one thing to another. And to end, one thing which is cool is that this is a very cool image. I talked about how knots were kind of like a spiritual thing. And these are three different loops, and they're linked in such a way that if you remove any of them, everything falls apart. So if you remove the green one, they'll slide apart, and if you remove the red one, they'll slide apart. But because there's 3 together, they'll stick together. So you can imbue dot theory with a lot of spiritual meaning, and people study these things and study what that means in prime numbers too. So that's what I wanted to say. There's some credits.
Okay, thank you, Prof. So now we get to the part you've all been waiting for, the awards for schools. So we'll start with the middle primary awards. So there's top schools for grades 4 and 5, and Dr. Celeste Johnson, who founded the contest, will be speaking out.
Welcome everybody, how exciting is this? So big congrats again to Dr. John Karev, Dr. Ranshad, is it professor now? It's just amazing. Can you believe that it was 7 years ago that a bunch of graduates, effectively, like people doing post and just graduate degrees, decided, it's about time that our institution, Wits, has a competition, just like other universities. There's no reason we shouldn't, but we're going to do it in a very special way. We're going to make sure that It also has universities. It's also got from grade 4 onwards. This is the first year that I've got 3 children, very different ages, who are all winning awards at this, and I'm super excited about that. But that's like a grade 4, a matric, and I've got no idea where they placed. That was all up to them to figure that out. But we've got this amazing thing, the fact that you're able to go to university and you don't have to stop thinking critically. You can keep thinking, why is it like this? And I think that's what keeps your mind strong and figuring out new strategies, and not just, you have to be curious, you've got to figure things out. What other things did we decide to do? We said, well, I think that even from primary school, kids should start learning how to write things down. It's not just going to be multiple choice or single answers. Learning just the discipline of writing from step to step. Lots of people think that problem solving is A, B, C, D, or E. And I guess, if you get 20%, that's average. If you get 60%, that's a little bit better. But to actually start writing it down and organizing one's mind. So that was a very special thing. What else did we say? We said, why don't we, have, instead of saying, you're disadvantaged based on gender or race or anything like that, let's say, in terms of quintiles, what is the thing? We want to say, are you like a school that gets lots of money, or you a school that doesn't? And if you're a school that doesn't get lots of money, which would be your quintile 1, quintile 2, so those would be your poorest schools, and then quintile 5 would be your upper end. But if you are a poor school and you are achieving well, then you deserve to be recognized. And we've got some awards for that. There were other things. Yeah, you don't have to pay. So as you know, the volunteers, no one gets paid to do this. We do it out of our goodwill. And John's done an amazing job of getting Jane Street, Sharp, Alan Gray to come and sponsor this. And there's no admin in terms of teachers having to run after people and say, please, can you give me 22.50 to enter this competition? They can just open it up to everybody and just get it done. Disadvantaged schools don't have to pay for it. So we're just super excited about that. Perfect. So let's see. Thank you. Done. Thank you. All right. So we're going to do things a bit differently this year. If you are a school over here, could you start making your ways down the way down the aisles, and then we'll start calling you up and we'll give you your prizes. So yeah, that way we're going to be a lot quicker. Can you all see? Okay, so there's Kuro Krugersdorp Primary School. Are people not hearing me? Is no one hearing me? I'm sorry.
Okay, so middle primary school winners, maybe come down while we...
If your school is over here, could you please start coming down just so that we could call you out quicker? All right. So in 10th place in Gauteng, we've got Kuro Krugersdorp Primary School. In 10th place Gauteng, we've got Glen Stanshire Primary School, so that was a tie. 9th place Gauteng, you can all start coming down. Kuro Serengeti. 8th place Gauteng, St. Mary's DSG Pretoria. 7th place Gauteng, a notable quintile 3 school. We've got Lakang Primary. In 6th place Gauteng, a notable quintile 3 school. We've got Dull Park Learning Academy. In 5th place Gauteng, we've got Midrand Primary. Okay. In 10th place overall, we've got Bridge House School Preparatory. In 10th place overall, we've got Sunningdale Primary School. In 10th place overall and 4th place in Gauteng, we've got Woodlands International College. Then, in 9th place overall and 3rd place Gauteng, please also come down, King David Linksfield Primary. In 8th place overall, we've got Windhoek Gymnasium Private School from Namibia. Yeah, we also open our borders to other places in Africa. How cool is that? In 7th place overall, we've got the Ambassadors School, OTA. In 6th place overall, we've got Edgemead. In 5th place overall, we've got, and 2nd place in Gauteng, we've got Red Hill. Woo! All right. In 4th place overall and 1st place in Gauteng, we've got Trinity House Preparatory School. Then, in 3rd place overall, we've got Glenwood Preparatory School. In 2nd place overall, we've got Somerset House. And in 1st place overall, we've got Sweet Valley Primary School. Okay. So like this. Okay, so this. Could we just ask the prize winners just to come and stick around with your certificate so we can get a group photo of everyone? Like now. Thank you. Okay. Could you just come to the left? Thank you. So this is the school awards. So yeah, that's perfect. If we could have like 1 or 2 representatives per school. Perfect. Moving on to the winning schools. Once again, if you come down, grab a certificate, come to my left, your right, so that we can have a little photo. So if your school is over here, please could you start coming down? So it's Kuro Serengeti. If you're collecting for the school, okay, so if you see your teacher come up and collect a prize, then you can stay in your chair. But if you don't have a teacher who's able to come and collect your prize, then you choose one person as your representative and you come down and fetch the certificate. Does that make sense? Okay, fantastic. So you're welcome to quickly head back to your chairs if you would like to. All right, so could one representative from each school from the following come, if you're here. So there's Kuro Serengeti, 10th place Gauteng. There's Teresano Moho Primary School. Wow, look at that. A quintile 1 school, 9th place Gauteng. I think that deserves a round of applause. Great, so we've got Dull Park Learning Academy, 8th place Gauteng, and a notable quintile 3 school. We've got King David Sanson, 7th place Gauteng. Midrand Primary School, 6th place Gauteng. Raleigh Modern Learning Environment, 10th place overall. King David Linksfield, 5th place Gauteng and 10th place overall. Model Private School, 9th place overall. Then, in 4th place in Gauteng and 8th place overall, got Trinity House, Rand Park Ridge. In 7th place overall and 3rd place, Gauteng, St. John's College. Then in 6th place overall, we've got Glenwood Preparatory School. In 5th place overall and 2nd in Gauteng, Laerskool Jan Cilliers. In 4th place overall, we've got the Ambassador School. In 3rd place overall, we've got Windhoek Gymnasium. In 1st place in Gauteng and 2nd overall, we've got Red Hill. And in 1st place overall, Sweet Valley Primary. Well done. Could we remind you, just one representative from each school, just head to our left over here, just for a photo quick. Perfect. We move on to the junior secondary winning schools. Once again, if you see your school up here and you have someone present, we'd love for you to come down. One representative per school if possible. Brilliant. I'll also just flip to this one. It's a little quick one. Awesome. All right. So we have a notable quintile 2 school, Lehao Secondary School. Then we've got a notable quintile 2 school, Rusumo High School. A notable quintile 3 school, Marabatota High School. Then we've got notable quintile 3 school, Kanyisa High School. What a wonderful lot of quintile schools. Right, in 10th place in Gauteng, we've got Kuro Thatchfield High School. In 9th place in Gauteng, we've got Saheti. In 8th place Gauteng, we've got Galabocha Secondary School. Is it Galabocha? Yeah. Okay, 7th place Gauteng, we've got Parktown Girls. In 6th place in Gauteng, we've got St. David's Marist. In 5th place in Gauteng, we've got Woodhill College. In 4th place in Gauteng, we've got King David Linksfield. Words for Acacia. Did I read that out? 3rd place, Gauteng, King David Linksfield. And then 10th place overall, we've got Stiastri College. In 9th place overall, we've got Machabeng International College. Same amounts. All right, and now. Woo! In 8th place overall, we've got Westerford High School. 7th place overall, we've got St. Henry's Marist College. In 6th place overall, we've got SA College High School. In 5th place overall and 2nd place in Gauteng, St. John's College. In 4th place overall, we've got Bishops. In 3rd place overall, we've got the Ambassadors College Orta. In 2nd place overall, we've got Rondebosch Boys. And in 1st place overall and first in Gauteng, we've got Radio.
So that was the Laridan Award, and maybe call on Jacob to give the... Jacob.
Okay.
Laridan was values, grades, and Wits in that education, and he's going to present the Fridgen Award.
Okay. So the Junior Secondary Awards, just so you know, that is the Laridan Award, and he was an incredible inspiration in Wits. So that's why it's named after him. And then Jacob is going to come and present the Peter Fridgen Award, and he was one of my lecturers, an absolutely incredible statistician. So, thank you.
So the winning schools, senior secondary, notable Quintal 1 school, Shielo. 10th place, Gauteng Patan Girls School. 9th place, Gauteng Jeppe Boys. 8th place, Gauteng King David Linksfield. 7th place, Gauteng Radford. 6th place, Gauteng Radio. Fifth place overall, Rand Park High School. 4th place, Gauteng Eden Glen High. 3rd place, Gauteng St. Stithias Boys. 10th place overall, GS Gishoma. 9th place overall, Marobatota High School. And 8th place overall, Kingsney. 7th place, Hilton College. 6th place, Petit Seminole Saint Vincent. 5th place overall and 2nd, Gauteng Sikulukile Math, Science and ICT School of Specialization. 4th place overall, Maru Apula. 3rd place overall, the Ambassadors College. Second place overall and first place, Gauteng St. John's College. First place overall, Nigerian Tulip Academy.
Okay. Okay, so after the excitement of the team awards, we're going to move on to the individual awards as a, to round it off. A few more ties this year, and so.
Perfect. If your name is on the list, could you please come down? So this is the middle primary kids.
There's a couple of kids like 9th and 10th, so that's positive.
Great. All right, we have a notable Quintile 2 learner, Kazimla Rachana from Exibeni Primary School. We've got a notable Quintile 3 learner, Katlego Si. Thank you. So we've got a notable Quintile 3 learner, Katlego Sihlon Gonyane from Ngonchane Primary. Then we've got a notable Quintile 3 learner, Oguhle Msezane from Del Park, LA. All right. Now in 9th place, Gauteng, it looks like we had a tie, hence why there's there's a few ninths. We've got Xiao Chen Jiang from King David Linksfield. We've got Ariela Sadeo from Red Hill. We've got Andrew Lombard from Trinity House. And we've got Michaela Johnson from Trinity House. And we've got Darshan Haripasad from Red Hill. We've got Rayansh Mohata from Red Hill, also in 9th place. We can give a round for all the 9th place learners. Then in 8th place, Gauteng, we've got Daniel Hewson from Trinity House. In 7th place, Gauteng, we've got Olivia Tate from Woodlands International College. In 6th place, Gauteng, we've got Hemming Opperman from Law School Jan Siliers. In 5th place, Gauteng, we've got Joel Castano from Trinity House. In fourth place, Gauteng, we've got Kairav Thorulsli from Trinity House. In ninth place overall, so overall winners now, also we've got a few ties. We've got Eli Ngowi from St. Andrews. We've got in ninth place overall and third in Gauteng, we've got Eden Rausal from private. Then from Glenwood Prep School, in ninth place overall, we've got Theusha Naidu. In eighth place and second place overall, eighth place overall and second in Gauteng, we've got Luna Wren from Red Hill. In seventh place overall, from Sweet Valley Primary School, we've got James Collin. And we're going to have a little bit more suspense for the last ones. In third place overall, we've got Jenny Lee from Sunningdale Primary School. Also in third place overall, we've got Jason Griesel from Somerset Primary School. Also in third place overall, we've got Mbele Hadebe from Model Private School. Also in third place overall from Edgemead Primary, we've got Kira Nuvaitz. First in Gauteng and second overall, we've got Simon van Weingaard. And first overall, we've got Sheldon Beloy. Once you have received your medal, could you please come to this side for a photo? We're doing a quick little maths example here of sorting from shortest to tallest. So if you see someone short in front of you, go ahead. If you see someone short in front of you, that's right. But if you see someone tall in front of you, you must go ahead of them. And teachers, if you want to have photos and quickly come and grab, I don't mind. You're welcome to quickly run and take a photo for your school. If you're coming to the front, it means you're happy for people to take photos of you. Fantastic achievements. All right, we're going to start moving on to the upper primary winning learners. If you see your name on the list, once again, you can start heading down.
Something wrong happened. Sorry. Crap. I'm checking. I think some of these were
Perfect. All right, I don't see anyone else moving, so I think most people have moved to the aisle, so I'm going to get started. So, a notable quintile 2 learner from Exibeni Primary School is Lingwambe All right. A notable quintile 2 learner, we've got Akona Mntamo from Exibeni Primary School. Another notable quintile 3 learner from Dal Park Learning Academy. We've got Utano Lungaka Klongwane. Then in 7th place, Gauteng, Red Hill School, we've got Nicholas Hilburn. In 7th place, Gauteng, from Jan and Leers, we've got Marcus Vasagi. In 7th place, Gauteng, from Red Hill School, we've got Brian Townsend. In 7th place, Gauteng, from Red Hill School, we've got Levi Lee. Then in 4th place, Gauteng, apologies if I'm not pronouncing, I'm trying. From Jan Leers, we've got Christian Luchmer. In 4th place, from Gauteng, from Trinity House Prep, we've got Yi Yun Evan Wei. In 4th place, Gauteng, from Red Hill School, we've got Jonah Kretzmar. In 3rd place, Gauteng, from Yeshiva College, we've got Ariva Vestin. In 2nd place, Gauteng, from King David Linksfield, we've got Daniel Malach. In 9th place overall, from Sweet Valley, we've got Eli Dalport. And also in 9th place overall from Sweet Valley, we've got Kian Buerta. In 8th place overall from Nigerian Tulip Inter College, we've got Chidera Harel Chidubem. In 7th place overall from Sweet Valley, we've got Ivy Williams. In 6th place overall from Graceland International School, we've got Temedira Janadu. All right, and we've got our 1st place Gauteng achiever and 5th place overall from St. John's College, Aidan Wright. All right, now in 3rd place overall, we've got Ella Luo from Glenwood Prep. And also in 3rd place overall from Nha Homeschool, we've got Sahasra Harinarayan. In 2nd place overall, I think this is from Nigeria, we've got Graceland International School, Jessie Lloyd. Is it from Cape Town? Graceland. It is Nigeria. And then in 1st place overall, from Homeschool, we've got Sarit Pechalmutu. All right. And now we've got a very special guest to come and present the next round of awards. It's Professor Arnold Knopfmacher. Perfect, so you can just press this button. There we go. So those learners can start coming up.
So this about.
Oh yeah, wait, actually, first we should. Yeah.
It's only after you. Say anything you want to.
So sorry, this which product?
This is the John Carpenter Prize for it's the junior secondary students.
Oh, okay. Okay, so if your name is on this, if your name is on the list here, please come down to collect your prize. And while you're doing that, I'll just say a few words. This prize is called the John Knopfmacher Prize, and not surprisingly, with that complicated name, that was my father. He was professor of mathematics many years ago, and in fact his lecturing career goes all the way back before anybody was born, except perhaps me. I was a toddler. This is back in 1964. He joined the maths department at Wits. There were maybe 30 members of staff, similar to what there would be even these days. But at that stage, only he and the head of the department had PhDs in mathematics, which is a big change because these days, if you want to join the department, even as a lecturer, you definitely need to have a PhD. Things were different back in those days. He rose through the ranks and eventually became a full professor and thereafter the head of school. While he was the head of school, that's around the time that I joined Wits, and because of the fact that they didn't want a conflict, I actually, although I also was a pure mathematician, I actually got my job in the applied maths department, which had a different head of department. Anyway, now having told you a little bit about my father, I'll call out the winning learners for junior secondary. Sonwe Bizi Gonkwa, the Korbani, a notable quintile 1 learner. In 10th place, Gauteng, Jashil Sadeo from Red Hill. In 9th place, Gauteng, Zhenchuan Liu from Red Hill. In 8th place, Gauteng, Yunling Zhu from Red Hill. In 7th place, Gauteng, Taran Kumalo from Red Hill. In 6th place, Gauteng, Matthew Malach from King David Linksfield. In 4th place, Gauteng, and 10th place overall, Richard Zhang from Saheti. In 4th place, Gauteng, and 10th place overall, Zihuan Liu from Red Hill. In 10th place overall, Joshua Freed from Bishops. In 3rd place, Gauteng, and 9th overall, Yi Shi from St. Stephen's College. In 2nd place, Gauteng, and 8th place overall, James Kerr from St. David's. 7th place overall, Cameron Broster from Rondebosch. 6th place overall, Fine Williams from Rondebosch. Okay, I think I need some assistance to get the next thing on the list.
So now it's going one by one because it's the top ones.
Ah, okay. 4th place overall, Nigerian Tulip International Colleges. It's Nikosh Chibedem Festus, and I apologize for the way I pronounced that name. In fourth place overall, Olivia Castledon from Somerset. First place Gauteng, and second place overall, Puyan Alex Sun from Red Hill. Second place overall, Adam Rassel from SACS. And finally, first place overall, Rowema Serge from École des Sciences de Gizenieri.
Let's wait for them. Yeah.
Sorry.
Can you I can give up this. Just say that you're going to say, well, don't press the button because otherwise they'll reveal the next windows. Just say that he's
Okay, so the next two awards. Wow, that was some echo. Okay, the next two awards are named after two professors. One Professor James Ridley from Wits, who's in Robotics now, and one of his students, Peter Sonak, who was an undergrad here and has gone on to be a professor at Princeton for the last 50 years. And Professor Said has worked with Prof. Sonak and met Prof. Ridley last night. So he's going to say some words about them.
Yeah, so I met Professor Sarnak, and he was one of my postdoc mentors. He always talks very fondly of Wits and of South Africa, and it's through him that I've had the opportunity to come here, and I think these awards are wonderful. And his mentor, when he started in mathematics, so he wanted to be a chess player, as far as I could tell, and Prof. Ridley is the one who turned him into a mathematician. And so it was a pleasure to meet Prof. Ridley yesterday, and I think both of these awards are, very great. So, yeah.
Okay, so we're moving on to the next category, which is senior secondary. If you're on this, slide, please come down and collect your medal and pose for a picture. Okay, so first we have a notable quintile 1 learner from TLLO, that's Siodiso Linda. We've got a notable quintile 2 learner from Pilisweni Secondary School, Kayalishle Mhlongo. We've got a notable quintile 3 learner from Marobatota High School, Dikhale Makwaneha Kamohelo. A notable quintile 3 learner from Marobatota High School, Leseho Makhoba. 10th place in Gauteng from Trinity House, Rand Park Ridge, Caleb Johnson. Ninth place in Gauteng from Radford House, Patrick Higgs. 8th place in Gauteng from St. Stithians Boys College, Nicholas Schmidt. 7th place in Gauteng from Trinity House, Rand Park Ridge, Jared Monchio. 5th place in Gauteng and 10th place overall from Trinity House, Rand Park Ridge, Ashar Johnson. 5th place in Gauteng and 10th place overall from St. John's College, Luke Brickhill. 10th place overall from Nigerian Tulip International Colleges, Ogenetejiri Esemitoje. 9th place overall from ES Kishoma, Nadine Ishumwewase. 7th place overall from Maruapula, Minal Tatamparambil Ranjit. 4th place in Gauteng and 7th place overall from Tesseract Homeschool, Kimaya Chana. 2nd place in Gauteng and 5th place overall from St. John's College, Xiaoyan Li. 2nd place in Gauteng and 5th place overall from Parktown High School for Girls, Amina Mayat. Okay, and then to our top 4, we've got in 4th place overall from Rondebosch Boys, Sebastian Stier. In 3rd place overall from Graceland International School, Agbo Adoga. In 1st place in Gauteng and 2nd place overall from King David Linksfield High School, Noah Greenblatt. And in 1st place overall from Westerford High School, Eli Williams.
Okay, you are, yeah, and you might have to grab a bunch of points. Okay, and looks like, finish with photos.
You remind me of that meme, the kids, you can buy them something nice for a $11. You're like, there's a cool
Okay, so now for the University Awards. Down. Okay, if you're an undergrad winner on this list, please come down and collect your medals. In 10th place in Gauteng, Bulale Makura from Wits. By the way, I apologize to anyone whose name I mispronounce. Also from Wits, Gabriel Felix Obelhauser, 9th in Gauteng. 8th place from Wits. 8th place in Gauteng from Wits, Rachel Sage. 7th place in Gauteng from Touch, that's the University of Pretoria, Siyabonga Malekwa. 6th place, Nelson Eli Pelsa. 5th place in Gauteng, Angus Clark from Tux. Now we have a three-way tie for 8th place overall. From Rwanda, Abel Puringimana, I am so sorry for mispronouncing that. Brock van der Westhuizen and Aiden Conradi, both from Stellenbosch. Okay, in 4th place, Gauteng, and 7th overall, Wayne Halungwane. 6th place overall from UCT, Aiden Gebi. And in 3rd place in Gauteng and 5th overall, Hamza Karim from Wits. Okay, now in 4th place overall from Stellenbosch, Jared Slater. 2nd place Gauteng and 3rd overall from Wits, Haider Ali Khan. In 2nd place, former winner Benjamin Klein from Stellenbosch. And in 1st place overall and 1st place in Gauteng, Mohammed Sarkhan.
Congratulations. Congratulations.
Okay, so that is functionally it.
In 3 and 2, right?
They're going to take their photos. If you've won a prize and didn't take a calculator, which is more or less everyone here, then you should come and get a calculator. And see you all next year. Oh, no, it's individual, senior, secondary.
No, I think I know.
Okay, all yours. It's Leseco. It's the top of the top three there. Where to get an Uber?
Can you show me on the map?
Sure. Yeah. If you give me 2 minutes.
First carteller. I think it's a rough yes.
It's a bursary from the Mental Foundation.
Or is it a service? Yeah. Sorry, give me 1 second. Everyone, I just have one more thing to announce, which is that we have a special award for the notable Quintile 3 learner at senior secondary level, Leseho Makhoba. The Musa Manzi Foundation has managed to organize that a bursary will be made available to Leseho for studies. Congratulations. Thank you.
Okay, so did you not get a prize? Wait, you saw the student's name? The name was there. The school's name. Right, so was the school's name on it? So sorry. So was the school called? Yes. Okay, so the student got an award. Okay, so then the student gets an award. Gets a So students don't get certificates. The school gets a certificate for school choice.
Okay, everyone. So if you didn't, if you were on the list of, if you were on the slides, you were someone whose name was mentioned. Then you can pick up a calculator, kindly sponsored by Shao, if you haven't taken one already. And otherwise, thank you everyone for coming.
Sorry, can I also pick up a calculator from our school?
If your school was one of the winners, then yes, absolutely.
So I got two calculators.
Yep.
Perfect, thank you. And are they all the same?
They're all the same.
Perfect. So it's all the black ones this year?
I think the only difference between them is the colors, but they're the same models.
Are they the solar ones?
I have no idea.
I'll have to look.